This is Monica and welcome to Snap Science tutorial. Today, I'm going to tackle about motion. But before that, let me show you a video that would help you understand my topic.
Hello friends, we all know what this line means. Its ups and downs are reflective of the various situations in our life, or rather our life itself. The blood is continuously flowing through our arteries and veins, supplying nutrients to various organs and fighting off invaders. The earth has been spinning since time immemorial, creating what we call day and night. But do you know what all these events have in common? They are in a state of movement or motion. Have you ever imagined what would happen if the aspect of movement was removed from these events? That is, if things stopped moving? The consequences are unimaginable. Even if we are faced with a traumatic event, we are told to leave the past behind and move on. These examples are few of many that serve to prove the phrase, movement is life. The different types of motion in all scenarios are studied by physics. To better understand this, let us take a walk in the park. While in the park, we see a lot of people doing various activities like walking, running, playing, cycling, etc. But what are all these people actually doing? And what do all their activities have in common? Well, they are moving, or they are said to be in motion. But what is this motion? We have all heard the phrase, time and tide waits for none. The part of the phrase which says waits for none indicates that for us to be regular, we have to do things on time. In other words, we have to move with time. This movement with time is called motion. If we pay a little more attention, we will realize that the phrase is also a comparison of ourselves to time. Thus, for a body to be in motion, it has to be compared to or related to something. Hence, when we see anything moving, we say that it's in motion. And if it's not moving, then we usually say that it's not in motion or stationary. But when we call things stationary, are they really stationary? These stationary objects are along with us on Earth. And as we all know, our Earth is not only rotating about its axis, but also revolving around the Sun. So isn't the Earth in motion 24/7? Yes, it is. And technically, if the Earth is in motion, then anything on it, including you, me, and all those stationary objects are also in motion. So even if these so-called stationary objects are moving, why do they appear stationary to us? Well, just like in life, the philosophy in physics too is the same. It's all about perspective, the way you look at things. If we consider stationary objects on Earth, then from our perspective, these objects do not change their position, because we too are on Earth with these objects. However, if we were astronauts and we were to view these same objects from space, then from our perspective, these objects would appear to change their position and now seem to be moving. This perspective position or relative position of an object is called inertial frame of reference. So what we are trying to get at through all this is the fact that the feeling of things moving and being stationary is because motion is relative. So now let's keep in mind that this concept of motion is not limited to objects on Earth alone, but also objects beyond it, like the solar system and galaxies in space. Let's understand this with a situation. Imagine you and your friend are sitting in a car which is moving. You will notice that your friend is still or not moving, but everything outside the car window is moving behind, like this man here. But if you see the same situation from the man's perspective, then you would notice that it's the car that's moving, and with it both you and your friend. This funny feeling is because, as mentioned earlier, motion is relative. Now let's be a bit observant. Though objects in the park are in motion either directly or indirectly, we notice not all motion of people or objects are the same. So now let's understand the different types of motion involved. In this situation, we can see that the person is jogging on a straight road. This type of motion, which occurs along a straight line, is known as rectilinear motion. Light from the sun, light bulbs and stars always travels along a straight line, and hence is the best example of rectilinear motion. Now, if we consider children playing with the ball, we see that when they throw the ball in air, it does not travel along a straight line, but rather takes a curved path. This type of motion is known as curvilinear motion, in which a body travels along a curved path. Can you recognize any other activities in your day-to-day life which involves curvilinear motion? The game of cricket is a good example. When we bat for a six, we notice that the ball follows a curved path as it crosses the boundary. Now that we know what rectilinear and curvilinear motion is, let's look at the scenario of a race and see what we can learn from this scenario. Here we see that there are kids participating in a race. At the end of the race, we see that there is a tie between 3 kids. The reason for the tie was because all 3 kids took the same amount of time to complete the race. The distance covered is also the same, as it's a fair race. Thus, we can conclude that all 3 kids took the same time to cover an equal distance. This type of motion, where bodies take an equal amount of time to cover equal distance, is known as translatory motion. While looking at the cycles and the car, we see that the tires are moving and their motion is along an axis. Such a motion is called rotatory motion or rotational motion, and sometimes also mentioned as circular motion. Other examples of circular motion are the merry-go-round and spinning tops, in which both the objects spin around a particular axis, which is at the center. Now, if we look at another bunch of kids who are swinging, we see that they are moving back and forth from a particular point, the center. This repeated motion of a swing going back and forth is known as oscillatory motion. Where else can we see oscillatory motion? We can see such motion in the pendulums of clocks, such as the grandfather's clock. If the rate of oscillation increases rapidly, then this motion now becomes vibratory motion. Examples of vibratory motion are musical instruments such as the guitar, violin, drums, etc. Another type of motion is periodic motion. As the name suggests, when a body repeats its motion after regular or constant intervals of time, it is known as periodic motion. Examples include the hands of the clock, Earth revolving around the Sun, and the Halley's Comet, which is seen only once in 76 years. Periodic motion can also be known as uniform motion because the movement is done in equal interval of time with constant speed. For example, if a man covers a constant length of 10 meters for every minute, then at the end of 10 minutes he would have covered a total distance of 100 meters. This is known as uniform motion. As long as this condition is fulfilled, the concept of uniform motion can in fact be applied to other types of motion as well. So if this type of motion is carried out in a circular path, then it is known as uniform circular motion. But what if the man is not covering a constant length and equal interval of time? Say that at times he walks slowly, taking more time, and sometimes he walks fast, taking comparatively a lesser time. Then these fluctuations or variations decrease the uniformity of motion and hence is known as non-uniform motion. This concept too can be applied to other types of motion. So what happens if this is carried out in a circular path? We get non-uniform circular motion. Simple, isn't it? So in this session, we saw how important and involved motion is in our life, that the concept of motion only comes into effect upon comparison of one body to another body, that motion is also of many different types. We hope that this session has been informative while arousing your interest.
Okay, enough for that. Now, let's discuss motion for you to truly understand this topic. Suppose you're seated in the library reading a book. How do you know that something is moving? You know you're not moving by looking at the other objects around you. In other words, your position does not change with respect to the shelves. A particular bookshelf or cabinet serves as your frame of reference, a point in space or an object that you assume is a fixed position. You observe how an object or objects move with respect to a frame of reference. Usually, the ground or any stationary object on it can be considered as a frame of reference when studying motion on Earth. So what is motion? Motion is considered to be the change in the position of the body with respect to a frame of reference. Since the frame of reference may vary, the motion of a body is relative. So now, let's talk about distance and displacement. Distance is described as the actual length from one point to another. It is usually expressed in meters or kilometers. Displacement is another quantity associated with motion. So what is the difference between distance and displacement? Distance is a scalar quantity. A scalar quantity has magnitude, but no specific direction is necessary to completely describe it. For example, a distance of 13 km has a magnitude of 13 km. Scalar quantities such as mass, time, temperature, and the other fundamental quantities mentioned in the first unit can be added arithmetically. Displacement, on the other hand, is the straight line distance between 2 points along with their direction. For example, 13 km due south. The magnitude is 13 km and the direction is south. Other vector quantities are velocity, acceleration, force, and electric field. A vector quantity cannot be treated as if it is an ordinary quantity, since its directional quantity has to be taken into consideration. The rules of ordinary arithmetic do not apply. Is it all clear? If it is, then let's go to the velocity and acceleration. Velocity is the rate at which an object changes position. Having both magnitude and direction makes velocity a vector quantity. Consider a car moving at 100 km per hour north and another car moving at 100 km per hour south. Although the cars have the same speed of 100 km per hour, their velocities are different because the cars are moving at different directions. So do you think it is possible for an object to move at a constant speed while its velocity is changing? Now let's see. Consider a man running around an oval track at a constant speed. His velocity is not constant because his direction of motion continually changes. If he runs at a straight path with constant speed, then both speed and direction of motion remains constant. A change in velocity can happen when either the speed or direction or both are changing. In a vehicle, there are 3 controls that can be used to change its velocity: the gas pedal, also known as accelerator, and the brakes are used to change the speed, while the steering wheel is used to change the vehicle's direction. Say for instance, you are riding a bus and the driver quickly steps at the brakes. The change in velocity is very abrupt. When this happens, the speed of a moving bus decreases abruptly. As a result, he may be thrown forward. If the change in velocity is less abrupt, you experience a smooth, even ride. Note that the rate at which velocity changes is called acceleration. To calculate the magnitude of average acceleration, the change in the velocity is divided by the change in time. The change in velocity is the difference between the final velocity and the initial velocity. Like velocity, acceleration is a vector quantity. If the body is moving at a constant acceleration, the distinction between average acceleration and instantaneous acceleration disappears. Acceleration is positive if final velocity is greater than the initial velocity for a particular time interval. Acceleration is negative if final velocity is less than the initial velocity for a particular time interval. So, that would be all for today's tutorial. Keep on watching Snap Science Tutorial and kindly visit our page www.snapsciencetutorial.com for more updates. Thank you.